There, it says B. And in this video, we are looking at the Unit 3, Lesson 1 cumulative practice problems for illustrative math geometry. So Unit 3 is all about similarity, and that means we are looking here at our first portion of it, which is going to be scale drawings. So for scale drawings, let's look at our first question. We have polygon Q as a scaled copy of polygon P. So it's always important to ask yourself which one is the original, which one is your pre-image and which one is your image. And in this case, if it's a copy of polygon P, that means P is the original. So it might help to write yourself a little note on that this is the original, and that Q is the copy. Just because you want to make sure that you do your scale factor here appropriately. So it says the value of X is 6. What is the value of Y? So if they're telling me the value of X is 6, I'm actually just going to write that here as 6. And they're asking me what is the value of Y. So we can set up a proportion here. I have 6 and 4 and Y and 3. We can either set up a relationship between the others or between the same pieces, either way. But a proportion is going to keep things in even amounts, so I would say, you know what, I like to use a part of an object over a part of an object equal to the corresponding pieces in a different one. So I'm going to use 6 over 4 and say that should be equal to Y over 3. And so now we can actually cross multiply here, and we would get 6 times 3 is 18, and 4 times Y is 4Y, so 4Y equals 18. So Y is going to be 18 over 4, which would simplify to 9 over 2. So we can say 9 over 2 is our value of Y. Now, they're asking us what is the scale factor, and the scale factor is a little bit different here. It's asking, like, what would we multiply this by? And so we're going to use values that they already gave us. That's going to be our 4 and our 3. So it's important to remember that the scale factor can be bigger than 1 or smaller than 1. And if our copy here is a smaller shape, then our scale factor should be smaller than 1. So that means we're going to basically do copy divided by original. So copy divided by the original. That is going to give us a scale factor of 3 over 4. Because it basically is going to tell us how to get the copy if we had the original size of the original shape. Okay, so moving on to question 2, we have figure F is a scaled copy of figure E. So E is the original, and F is the copy. It does help me to keep track of these, so I'm not just writing them to get you used to it. It helps me too. And we are going to then answer some of these questions about it. We know a couple of the values. They're just listing some facts for us here. That's all that this is. This is nice facts for us, but we want to select which of these equations is true. So just like in number 1, how I was able to set up a proportion here with 6 over 4 and Y over 3, we want to select all true equations here because that's not necessarily the only equation I could have set up. So let's look at what we have first. They're first saying 6 over 3 equals 4 over a. So we at least want to make sure we're being consistent, and this one looks like what I was doing in the previous one. I always like to look at the image here. They're saying 6 over 3 is going to be the same as 4 over a. And I agree. I'm comparing the horizontal one to the vertical one in one shape, to the horizontal and then the vertical in another shape. So agree with that one, which means I am going to say that one is true. But we can do this a couple different ways as long as we're being consistent. So let's look at B. They say 6 over 4 equals 3 over a. So they're saying 6 over 4 is equal to 3 over a. This is also going to be true because we're comparing the horizontal ones from the original to the copy to then the vertical ones from the original to the copy. So as long as we're doing corresponding pieces and we're going in the same order, then this is okay too. It would have been incorrect if we said 6 over 4 is equal to a over 3. That would not have worked because we would have gone in the wrong order. We would have compared original to copy, but then copy to original. We want to make sure that we're going in the same direction when we're comparing piece to piece. So B is true. This one was also correct. And these are actually the only two that are going to be true for this question. We can look at the rest of them and kind of explore why they're not true. So 3 over 4 and 6 over a. 3 over 4 is comparing vertical to horizontal from the original to the copy. And then 6 over a is comparing horizontal to the vertical from the original to the copy. So we can't cross over our arrows either. Not going to work. So that one doesn't work either. If we did 6 over 3 equals a over 4, they're saying 6 over 3 equals a over 4. Again, my arrows are going not really in the same direction. So not going to work because they're not comparing similar amounts. If we look at E, 6 over 4 is a over 3. That was the example I gave of something being incorrect with my arrows going wrong directions. So not going to work. So far we've looked at these ones as not being true. Let's look at their last one. 3 over 4 equals a over 6. So 3 over 4 is equal to a over 6. Again, my arrows are going different directions and they're crossing over each other. I am not using a corresponding part here. I'm using vertical to horizontal, so it's not going to work either. But if we looked at these two right here, we should have 6 over 3 and 4 over a. 6 over 3 and 4 over a. These go the same direction, so they're good. And 6 over 4 and 6 over 4 and 3 over a both go the same direction as well, so that's good. That's the best way I can explain it. I like to use visual things as I go. It helps me out. So let's keep going and solve some proportions down here. We're going to show all of our work. So I will be a bit more detailed with this. Oops. That's my notebook, and that's my blank copy. This is the copy I'm working on. Sorry about that. Went to hit a pen and I hit a different title of a different page I was working on. So let's solve each equation and show all of our work. I'm going to zoom in here and just show my work for each piece. So I'll do these in blue and I'll use a smaller pen. So I'm going to do 2 times 15. This is going to be the same as 5 times x. So I'm not going to show the cross multiply part for each one, but that is the process that I'm doing, is I am cross multiplying. So 2 times 15 is 30, and 5 times x is 5x. We can then divide both pieces by 5. 30 divided by 5 is 6, so our value of x is 6. Okay. For b, we're going to do the same thing. I'm going to say 3 times x and put that one on the left. So 3x equals 7 times 4. So 3x, 7 times 4 is going to be 28. I'm going to take both sides and divide by 3. So x, in this case, 28 divided by 3 does not simplify. So I'm just going to leave it as 28 over 3. Fractions are okay to leave as improper numbers. Just because we call them improper does not mean that they're unacceptable as solutions. So that brings us to the next one, which is C. We're going to do 7 times x and 5 times 28. Okay, so I like to put my variables on the left, so I'm going to do 7 times x, so 7x on the left part. But 5 times 28 is going to be a pretty big number. But I believe it should be 140 without even doing that on a calculator, because 5 times 30 is just 5 times 3 with the 0 added on. And 5 times 3 is 15, with the 0 is 150. But I am not actually using 30, I'm only using 28. So I have to take 2 5s out, which is a 10. It's going to be 140. That might have been a jumble of nonsense numbers to you, and that's okay. I just wanted to walk through the process of how I did that in my head. It is going to be 140. You can check me on a calculator with that one. I promise it works out. From here, we would take each side and divide by 7. Oh, I guess I didn't show my whole work, so hang on. I should probably move this down and include that I did, even though I did it in my head, I should include that I'm doing 5 times 28 to give me the 140. But when I divide by 7 on each side, x is going to leave me with 20, and that is the answer for part C on this question. For D, we're going to do the same thing. Oops, I meant to zoom in here. Okay, so 11 times x. I always like to do the part with the variable first, so sometimes you'll see me doing from top to bottom or from left to right. Like I might start and be a bit inconsistent, but I like to do the part that has my variable first. So I'm going to put 11x, but that means on the other side I have 4 times 5. So 11x is equal to 20, and we need to divide both sides by 11. And this is not going to reduce, we are just going to leave it as 20 over 11. Again, it's an improper fraction, but it is an appropriate answer. So those are our 4 answers for this question. Which brings us to question 4. We're going to select a shape that has 180-degree rotational symmetry. So rotational symmetry for 180 degrees means we can flip it all the way over, rotate it 180 degrees, and it will map onto itself. So trapezoid, I like to use visuals for these, so a trapezoid is something that has 2 parallel lines. So kind of like this. And the other lines are just not parallel. If I rotate that shape around 180 degrees, not going to land on itself. An isosceles trapezoid is similar, but it has, if I could draw straight lines correctly, it's going to have 2 sides that have the same angle at the bases, but it's still not going to work because I would have a shorter side flipped upside down onto the bottom side, and a quadrilateral is really any shape that, like, the only definition of this is four sides. So that does nothing to tell us about the rotational symmetry. A rhombus, however, has four sides that are the same length, meaning it's kind of like a diamond shape. And so this one is going to be the one that has 180-degree rotational symmetry. If we flipped it upside down, it would land neatly on top of itself if we spun it around. So question 5 is now going to ask us to name a quadrilateral in which the diagonal is also a line of symmetry. So a line of symmetry implies that we have reflectional symmetry or reflection symmetry. So reflection, not rotation. And we want to explain how we know the diagonal. This, again, our answer is going to be a rhombus. So we did talk about properties of parallelograms, and in a rhombus, I think we also talked about how the diagonals bisect the angles. And if the angles are cut in half, that means if we reflected over that diagonal, that one half of the angle would map onto the other half of the angle. We already know with a rhombus that all of the sides are the same length, so the sides would map onto each other. It's just making sure that our angles match up that can be tricky sometimes, and both of the diagonals of a rhombus bisect the angles. So this is the type of shape where the diagonal is a line of symmetry. So we would say, in order to explain this, let's actually use some math words here instead of my basic description. So we can say the diagonals of a rhombus bisect the angles since all four sides are congruent. Sides are congruent, and we also know that opposite angles are congruent. So we're going to have an opposite angle that would reflect over and onto the other angle of the rhombus, and then the bisected angles ensure that those ones specifically fold onto each other as well. Since all four sides are congruent and opposite angles congruent. Each piece should reflect onto we'll say a corresponding piece. So the important part here is we did need the shapes to have congruent sides, but also to have bisected angles, and to have those opposite angles congruent. So really a rhombus is the only one that works for this. So for question 6, we have an isosceles triangle, DAC. And in this isosceles triangle, AD is congruent to AC, and AB is an angle bisector. So that's already labeled for us. They gave us our congruence marks, and they gave us that our angles are bisected, so those have congruence marks. We want to say, how does Kieran know that AB is a perpendicular bisector of CD? So, how does Kieran know that this is a perpendicular bisector, meaning that these parts are going to be congruent? So, this is actually part of the perpendicular bisector theorem, that any point, we're going to say A, in this case, I'll highlight it instead of circling it. If we have a point that is an equal distance away from the endpoints of a segment, then that point must lie on the perpendicular bisector of that segment. So we can also prove some of these things with like side to angle side, I believe, because we have a shared side in the middle here. And with side angle side, we would know that these two middle angles would need to be congruent with each other. And since they make a straight line, they would have to be 90 degrees. But I think it's a great time to talk about the perpendicular bisector theorem. So we can say perpendicular bisector theorem. If a point is an equal distance away from the endpoints of a segment, then the point must lie on the perpendicular bisector of the segment. Now I'm also going to talk about the side angle side stuff here, just so that you have that explanation, but I am going to highlight the things I just wrote to color coordinate with this. So if a point, and in this case, literally point A, is equal distance away from the endpoints of a segment, and in this case, the endpoints of the segment are A and B, or I'm sorry, A is the point, its equal distances away from C and D, then it must lie on the perpendicular bisector of the segment. That is this, but it may also want us to basically be proving the perpendicular bisector theorem. So we can also say triangles, I'm going to actually label this stuff right here in red so it makes more sense with what I've shown sort of on my triangle in red. So I have the two different pieces kind of saying the same thing. So triangle ABD is going to be congruent to triangle ABC by side angle side. This is because AB is congruent to AB, so it's the same segment. plus we have the other marked things. So that means angle ABD is congruent to angle ABC by CPCTC. So those two, the segment in the middle is shared, so it's a shared segment. That gives us the SAS. And then we have CPCTC for the angles down there at B. Since they are also supplementary, they are supplementary and congruent. Both are 90 degrees. And then I can also say that DB and CB are congruent by CPCTC as well. So DB is congruent to CB by CPCTC, and being that the segment is in two equal parts and that those angles are 90 degrees means that A lines on the perpendicular bisector, so we can say therefore AB, getting my letters mixed up here. That's always important, always double check yourself. AB is the perpendicular bisector of DC. So two separate explanations that both work. It really just depends on whether they want us to prove the perpendicular bisector theorem or to use the perpendicular bisector theorem. So blue is using it, and red would be what we would use to prove it. So a little bit long of a question there, but wanted to show you both pieces. Oops. Okay, so continuing on, we're going to look at question 7. So lines F and G are parallel, and we have a transversal going through them. We're going to select all angles that are congruent to angle 1. So I'm going to start by highlighting angle 1 in green, and then anything that is congruent to it for appropriate reasons, I'm actually just going to highlight in blue. So I see that 4 is vertical with it. I also see that 4 and 8 are corresponding. So vertical and corresponding angles are all congruent. And then 8 is also vertical with 5. So looks to me like I have 4 and 5 and 8. So I should be using D, E, and H for my answers here. And I mean, I guess angle 1 is also included, so I didn't realize for a second that they included that as an answer here. So we're going to say that, yeah, it's going to be congruent to itself, because any angle or segment will always be congruent to itself. But hopefully my highlights and everything make sense why. If you really want to go in depth, you can write reasons next to each of them, but it doesn't ask us to do that, so I'm not going to go that in depth. And that is actually the last question on this assignment, so thank you for sticking with me through this. This has been the Unit 3, Lesson 1 Cumulative Practice Problems for Illustrative Math Geometry.